Everyone keeps saying, we're going to Mars, like it's just the next stop on a long road trip. But the reality behind that slogan is a lot darker than it sounds. Once you leave Earth, you're locked into a years-long ride with no exit, no rescue, and no life help if anything really serious goes wrong. In this video, we're going to strip away the posters and the hype and look at what a human Mars mission actually means for your body, your mind, your ship, and your chances of ever seeing Earth again. But before we continue, please subscribe to the channel to give your support. Let's continue. Start with the basic distance. On the very closest approach, when Earth and Mars happen to be on the same side of the Sun and roughly lined up, the gap can be about 54.6 million kilometers, around 34 million miles. That's the absolute best case. On the worst alignment, when they're on opposite sides of the Sun, the distance blows out to about 401 million kilometers, roughly 249 million miles. Most of the time, you're not at the best or the worst, you're somewhere in between, with an average separation of about 225 million kilometers, around 140 million miles. These aren't just trivia numbers, they set the scale of everything that follows: how long the trip takes, how much fuel you need, how cut off the crew is. Now link that to time. With current rocket technology, you do not get to Mars in days or weeks. A realistic one-way trip is roughly 7 to 10 months, something like 200 to 300 days, just to arrive. That's with efficient trajectories, with everything working. And that is only the outbound leg. You still have to stay at Mars for a while because of orbital alignment, and then you have to make another long trip back. In total, you're looking at something like 2.5 to 3 years away from Earth. So when someone says, let's send people to Mars, what they're actually saying is, let's lock a small crew into a tiny artificial world for almost 3 Earth years with no quick way home. You might think, fine, it's far and it takes months, but at least we can choose a date and go. Why can't you just decide, launch in July and be done with it? Because you're not flying to a fixed target. You're trying to intercept a moving planet that's orbiting the Sun at its own speed. To do that without using absurd amounts of fuel, you normally use what's called a transfer orbit. The classic version is a Hohmann transfer. In plain terms, you drop the spacecraft into a big oval path around the Sun, starting from Earth's orbit, and that oval is tuned so that you reach Mars's orbit right when Mars is there. That alignment between Earth, Mars, and the transfer path only lines up well about once every 26 months, and that's your main launch window. During that window, if you launch at the right time, you can reach Mars with a reasonable travel time and a reasonable amount of propellant. Still huge, but not insane. Miss that window because a rocket had a fault or funding slipped or some key system wasn't ready, and you don't just delay by a week. You can be pushed back by over 2 years. Yes, you can force a mission outside the ideal window, but then the energy goes up, the required fuel goes up, and the travel time can get even worse. So the universe basically says, you can go to Mars, but you get these narrow, rare chances, and if you're not perfect, you wait. Let's say you do catch that window. Your launch works and your ship is on its way. A natural question is, if something goes badly wrong halfway there, can't you just turn around? We're used to this idea from planes and moon missions. To see why Mars is different, compare it to the moon. The moon sits about 384,000 kilometers, around 239,000 miles. The Apollo missions took about 3 days to get there. On that timescale, if you had a serious issue mid-flight, you could change the trajectory and be back at Earth in a handful of days. And that's terrifying, but it's within a human emergency frame. Now push that out to Mars. Instead of 384,000 kilometers, you're dealing with tens or hundreds of millions of kilometers. Instead of 3 days, you're roughly 200 days out in deep space. The trajectory you're on is designed very precisely, not just to leave Earth, but to reach Mars with the correct speed and angle, so you can enter orbit or descend. By the time you're a few months into the journey, your velocity and direction, relative to both planets, are locked into that plan. To turn around in any meaningful way would mean changing your speed by huge amounts, which would require a ridiculous amount of extra fuel that you did not carry because every extra kilogram was already painful to launch from Earth. In practice, once you fire the engines for the big burn that sends you from Earth orbit onto a Mars intercept path, you have committed, not just emotionally, but physically. If a critical system fails at day 120, you're not choosing between going home and going on, you're choosing between trying to patch it with what you have or dying. The mission architecture simply does not include a quick abort mode. There is no 3-day return. The distance and the energy make sure of that. At this point, you might say, all right, even if we're locked in, can't we at least go faster so we spend less time in danger? Why can't we just build a more powerful rocket, cut the travel time, and reduce the risk from radiation and system failures? To answer that, you have to look at speed in a more technical way. To make the typical 225 million kilometer journey in around 8 months, the spacecraft's speed around the Sun, compared to Earth, changes by tens of kilometers per second over the different phases. If you convert that across the burns and maneuvers, you're talking about changes on the order of 30,000 to 40,000 kilometers per hour, around 19,000 to 25,000 miles per hour. For comparison, a rifle bullet might be doing about 1,000 meters per second, which is roughly 3,600 kilometers per hour, about 2,200 miles per hour. The engine work across the Mars mission is dealing with velocity changes that in total are more than 100 times that. And yet, even at those speeds, from the human perspective, you still crawl through space for most of a year. If you push the mission to go significantly faster than the standard transfer, you pay a price. You need more engine power, you need more propellant, which makes the spacecraft heavier, which then needs even more propellant. Structural loads go up, heating loads at departure and arrival go up, and your safety margins shrink. The faster you try to brute force it, the more tightly you bind the mission to extreme engineering assumptions that have to hold for months with no failure allowed. There's another layer. Even if the ship is intact, the crew trained, and the timing perfect, you still hit a wall that no rocket can fix: the speed of light. On Earth, when you send a command to a satellite in low orbit, the radio signal, which moves at light speed, gets there in a tiny fraction of a second. It feels instant. Talking to the moon, the delay is around 1 and a bit seconds each way. Noticeable, but fine. Mars changes the game again. Depending on the positions in their orbits, the one-way signal delay between Earth and Mars ranges from about 4 minutes up to about 24 minutes. That means a basic back-and-forth exchange, you ask something, they reply, can take anywhere from about 8 minutes to almost 50 minutes. Think about what that means for a real emergency on board. A valve is stuck, a fire has started, someone is injured, or some sensor is showing confusing data. On the International Space Station, you can talk to Mission Control basically in real time, and you have cargo ships that can bring spare hardware in weeks. On a Mars transfer, you have a small crew, a limited set of tools and parts, and a support team that is delayed by the laws of physics. There is no live voice saying, "Stop, don't touch that," before you flip the wrong breaker. By the time advice arrives, the situation may have already crashed one way or another. So the crew is not just assisted from Earth, they are, in practice, their own first and last line of defense. Put all of that together, and the first big truth hits you. Mars is not just far. The distance, the orbital timing, the lack of abort options, the brutal speed requirements, and the light speed delay all combine into a mission profile where once you go, you are committed for years with no fast escape and limited help, in an environment where small mistakes can kill you. And remember, this is before we talk about how much fuel you need, how big the rocket must be, or how badly the math of rocketry punishes you for every extra kilogram you want to carry. So the next question is simple and nasty. If just crossing the gap is this hard, what happens when you ask, how much energy do we actually need to do all of this, and how much fuel does that really mean? Because the moment you dig into that, you meet the next enemy, the rocket equation. And that thing does not care about your dreams of walking on red sand. You know what really decides whether a Mars mission lives or dies, long before anyone plants a flag? The number that quietly kills you is how fast you need to go and how much fuel that speed really costs. People talk about courage and vision, but rockets don't care about that. They care about something called delta V, and delta V decides how big, how heavy, and how insanely complex your Mars stack has to be. Delta V, said in plain language, is the total change in speed your spacecraft must produce over the whole mission, not just launch speed off the pad, not just the boost toward Mars, all of it added together. From Earth's surface to low Earth orbit, then from orbit onto a path toward Mars, then slowing down to get captured by Mars's gravity, then landing, then taking off of Mars, then getting back on a trajectory to Earth, then finally handling re-entry at home. Each piece needs its own chunk of speed change, and those chunks add up. For a full Mars mission, you're looking at well over 15 kilometers per second of total delta V, depending on the exact design. That's more than 15,000 meters per second, or over 34,000 miles per hour of accumulated speed changes your engines must provide across the whole chain. Here's the part that hurts. The relationship between that total speed and the fuel you need is not gentle. It's not add a little more speed, add a little more fuel. The rocket equation is exponential. In simple terms, every extra meter of second you demand at the top of the stack multiplies the amount of propellant and structure you need at the bottom. You add fuel to get more speed, but then you need more fuel to lift that fuel, and more tank to hold the tank, and more structure to hold the tank, and you're stuck in a loop. A small increase in required delta V can translate into many extra tons of propellant, and that mass has to be launched out of Earth's gravity well first, which is already the most expensive step. So even before you deal with life support, crew, or cargo, the raw energy bill is pushing your rocket toward ridiculous size. So how do you even build a machine that can deliver that much total speed without being completely absurd? You don't do it with one big tank and one engine. You break the rocket into stages, and each stage is basically a giant disposable bomb of propellant that you drop once it's empty. That's why rockets like Saturn V look the way they did. Saturn V, the launcher that sent Apollo crews to the moon, was about 110 meters tall, around 363 feet. It lifted a relatively small mass of humans and hardware to the moon for missions that lasted days, not years, and never left Earth's neighborhood. And even that was right at the edge of what 1960s engineering and budget could pull off. A Mars mission needs much more mass in space. You need a larger habitation volume, extra food, more water recycling, more oxygen systems, better radiation shielding, a lander that can get humans safely down through Mars's thin atmosphere, and an ascent vehicle that can get them back off the surface. You also need spare parts, tools, and margin. Trying to put all of that on top of a single rocket is not realistic, so you start splitting the mission across multiple heavy lift launches. One launch sends a habitat module, another sends a cargo lander, another sends a propulsion stage, another sends fuel, and then you assemble or refuel things in Earth orbit. Now your Mars rocket is no longer one vehicle, it's a whole stack of missions spread over months or years. Each heavy lift rocket is massive on its own, in the Saturn V or bigger class. Every one of those launches has to work. If one critical launch fails, maybe the propulsion stage is lost, or the ascent vehicle, or a key piece of life support hardware, the whole Mars mission architecture can collapse. You don't just lose one rocket, you potentially lose the window, the strategy, and the billions tied to that stack. Staging solves part of the energy problem, but it pushes you into a logistics problem that's just as dangerous. And that's only for getting there and setting up. What about coming back? Where do you put the fuel for the ride home? If you try to carry it all from Earth, the mass at liftoff explodes. You're not talking about a big rocket anymore. You're talking about something that starts to look like a flying skyscraper of tanks and engines, because you're carrying fuel to push fuel to push fuel. Each extra ton of return propellant has to be lifted through Earth's 1G gravity, with all the structural reinforcement that needs. To get around that, most serious Mars plans lean on an idea called in situ resource utilization, ISRU. Instead of carrying all your return fuel from Earth, you send hardware ahead of the crew. That hardware lands on Mars and uses the planet's own resources, carbon dioxide from the thin atmosphere and water ice in the ground, to manufacture propellants like methane and liquid oxygen. If it works, by the time the crew arrives, their ascent vehicle is sitting on the surface with full tanks, waiting. That saves an enormous amount of launch mass from Earth. The problem is, this is still mostly theory and small-scale testing. We have not yet deployed a full-scale, crew-critical ISRU plant on Mars, run it for years, and proven that it can reliably spit out tons of fuel on schedule in Martian dust, cold, and radiation. For a real mission, this system is not optional. If the plant underperforms or fails silently or produces contaminated propellant, the crew could land and discover that their ride home is a dead asset. You're now tying the survival of the crew to a complex industrial process running on another planet with no maintenance team on site until after it's already supposed to have worked. Even if you assume all of that somehow operates as designed, there's one more trap, and it's a nasty trade-off you cannot dodge: safety versus mass. For a mission this long and this remote, you want redundancy. You want multiple engines, backup navigation systems, extra computers, spare life support hardware, and healthy fuel margins. You also want shielding against radiation and mechanical backups in case something breaks. Every one of those nice-to-have safety features adds kilograms to the spacecraft. The more hardware you add, the heavier the vehicle becomes. Because rockets live under that exponential fuel law, every extra kilogram you add high up in the stack forces you to add many kilograms of propellant lower down, plus more structure to hold it all together. So your backup gear requires more fuel, your extra fuel requires more tank, the tanks require more structure, and suddenly you're back in the same spiral, where mass drives more mass. On the other side, if you start stripping redundancy to save weight, you simplify the rocket a bit, but you expose the crew to single-point failures. One pump fails, one valve sticks, one computer dies at the wrong moment, and there's no backup ready to take over. The result is a vicious loop. Make the mission robust, and the vehicle becomes so heavy and expensive that building and launching it with current industrial capacity looks almost out of reach. Cut it down to something launchable and cheap enough, and now you're betting human lives on a system with thin margins across 1,000 days in deep space with no rescue. And remember, all of this is just the mechanics of moving hardware and fuel around the solar system. None of it solves the fact that once you fought the rocket equation and won, your crew still has to sit for months in a radiation environment that never turns off. So the next question hits even harder. Even if you somehow build the rocket, line up the launches, and get the mass under control, what does it do to a human body when you park it outside Earth's magnetic shield for years, with almost nothing between your cells and high-energy particles from the sun and the galaxy? Space looks empty, so why is it one of the most dangerous radiation environments you can put your body in, even when nothing is happening? Outside Earth's magnetic field, you are basically sitting inside an invisible particle storm that never turns off, and the Mars mission doesn't dip into that storm for a few days. It parks your crew in it for years. Start with what you're actually being hit by. Out in deep space, beyond the protection of Earth's magnetic shield, you get two main radiation sources. First, galactic cosmic rays. High-energy particles that come from outside the solar system slamming through you at close to the speed of light. Second, solar particle events. Big outbursts from the sun where protons and other particles are fired out during flares and coronal mass ejections. Both are made of real matter, not light, and when they hit your cells, they can break DNA, damage tissues, and trigger long-term health problems. NASA estimates that a full Mars mission, outbound cruise, time on the surface, and return could give an astronaut a total dose on the order of 1 sievert. In simple terms, that's 1,000 millisieverts, and that's roughly the full lifetime career limit many agencies set for astronauts. 1 sievert doesn't instantly kill you, but it significantly increases your risk of cancer and other problems over the rest of your life. You're not just getting a tan, you're rewriting the statistics of how likely you are to get serious disease later. Look at the trip itself. Measurements from probes and test missions suggest that in deep space, on the way to Mars, a crew could be taking in around 1.8 millisieverts per day. Per day! That is several times higher than what you'd get on Mars's surface, and much higher than astronauts get on the International Space Station, which still sits inside part of Earth's magnetic protection. You stack that daily dose for 200 to 300 days on the way out, and again on the way back, and you can see how the numbers climb very fast. The cruise phase alone is already eating a huge chunk of that one Seavert budget before you even step on Mars. So the obvious question is, does it get better once you land? Do you at least get some kind of break on the surface? The answer is a little, but not enough to relax. On Mars, the thin atmosphere and the small amount of natural shielding from the ground reduce the dose compared to deep space, but not to Earth levels. Rovers on Mars have measured surface radiation of around 0.64 to 0.7 millisieverts per day. Spread that over a year, you get somewhere around 240 to 300 millisieverts per year. For comparison, the average background radiation dose for a person on Earth in a year is on the order of a few millisieverts. So you're talking about something like 40 to 50 times higher than what your body has evolved to handle at sea level. Now plug that into a mission timeline. You pick up maybe a few hundred millisieverts cruising out, then you spend a year or more on Mars, taking another couple hundred, then you cruise back and stack more on top. Your lifetime dose climbs toward that 1,000 millisievert region. Every extra month in that environment moves your odds a bit more in the wrong direction. You walk around doing daily tasks, but there's a kind of health time bomb quietly ticking in the background, built from particles you can't see or feel in real time. The usual answer to radiation is obvious. Put more material between the crew and space. So why not just wrap the spacecraft in thick shielding and fix it? Because shielding is not free. In fact, it's one of the most painful trade-offs in the whole mission. To seriously cut down the deep space radiation to safer levels, models suggest you want on the order of 20 to 30 grams of material per square centimeter around your habitat. In more normal language, that's several centimeters of aluminum, or a good thickness of water or other hydrogen-rich material over every part of the crew volume. Turn that into mass and it explodes. When you cover a habitat with that much material, you're talking about many tons added to the structure. Picture every square meter of the walls carrying weight equivalent to a small car. That's the kind of mass you're dealing with. All of that has to be launched out of Earth's gravity well. Remember the rocket equation from before. Every extra kilogram of shielding at the top means multiple kilograms of propellant lower down, plus the structure to hold it. If you try to push radiation down to comfortable levels by brute force shielding, you quickly end up with a ship that's too heavy and expensive to launch with current rockets. Because of that, many designs compromise. They use partial shielding, put water tanks around sleeping areas, or create a storm shelter where the crew can hide during a big solar outburst. That helps with short, intense events from the sun, but it does less against constant galactic cosmic rays, which are so energetic they can punch through most normal materials and even create secondary radiation when they hit the shielding. So you're stuck. Thin walls mean less mass but more radiation. Thick walls mean better protection, but a rocket that might never leave the pad. This leads to a blunt comparison that makes the danger easy to understand. On Earth, a chest X-ray might give you about 0.2 millisieverts. A Mars mission, end-to-end, could deliver around 1,000 millisieverts. That's like being handed several thousand chest X-rays spread out over a few years. And you're not lying still in a hospital while that happens. You're supposed to be operating complex equipment, fixing systems, doing science, and dealing with emergencies, all while your cells accumulate damage in ways that aren't obvious day to day. The worst part is, there is no perfect practice range for this on Earth. You can simulate parts of it, you can expose animals and cells to radiation in labs, you can put astronauts on the ISS and monitor them, but that's still with Earth's magnetic field helping out, and for shorter durations. We don't have a true long-duration, deep space radiation analog with humans at Mars mission lengths to really know how all the risks stack together. So you're sending a crew into a situation where the radiation models are educated guesses, not fully proven limits. And even if every person on that ship accepts the cancer risk, the cataract risk, and the cardiovascular risk, there's another layer. Radiation also affects the brain, cognitive performance, and fine motor skills. You are asking people to work at peak precision under long-term stress in an environment that is actively degrading their biology. And you do not get a reboot if it turns out you aimed a little low on the shielding. So now you have a crew that's taken a huge radiation hit just across the gap and stay alive on the surface. The ship is lighter than you'd like because you couldn't afford perfect shielding, and every extra day you stay, the dose goes up. And that's still only one part of the biological damage. The next question is simple and brutal. Even if you somehow manage the radiation, what happens to a human body when you strip away normal gravity for months, weaken bones and muscles, and then drop that body onto a planet where the gravity is wrong and the work is hard? How do you send a human body to Mars when the first thing space does is start taking that body apart piece by piece before it ever sees the planet? Microgravity is not floating around and looking cool. It's a slow, continuous attack on all the systems you rely on to stand up, think clearly, and not break when you fall over in a bulky suit. Start with your bones. On Earth, you live in 1G. Your skeleton is loaded all the time, even when you're just standing still. Your body responds by keeping bone mineral density at the level that matches that load. In microgravity, close to 0G, that signal disappears. The body basically decides, we don't need all this dense bone anymore, and starts resorbing it. Data from space stations show that astronauts can lose around 1 to 1.5% of bone mineral density per month in weight-bearing bones like the hips and spine. That doesn't sound huge in 1 month, but stretch that over a Mars transfer. On a 7 to 10 month trip, you're talking about something like up to 10% loss in the worst bones. That is the kind of reduction you'd normally see over many years of aging on Earth. But here, you're hitting it in less than a year while still relatively young and supposedly at peak performance. And this isn't just about being a bit more fragile. Lower bone density means higher fracture risk if you fall, slower healing if you get injured, and more calcium in your bloodstream, which can affect kidneys and other systems. You arrive at Mars with a skeleton that is literally weaker than when you left, and you still have to walk, carry gear, and handle hard landings. Bones are only half of the mechanical story. The other half is your muscles. On Earth, your leg and core muscles are constantly working just to keep you upright against 1G. In microgravity, that baseline work drops to almost zero. Even if you feel like you're moving around a lot inside the spacecraft, there's no constant downward pull to resist. The body responds in a predictable way. It starts shrinking muscles it doesn't think it needs. Even with current exercise programs on the ISS, which can be around 2 hours a day on treadmills, resistance devices, and bikes, astronauts still show significant muscle atrophy on long missions. We're talking about tens of percent of loss of strength and mass in some muscle groups. Now picture the sequence. You leave Earth, experience almost 0G for 7 to 10 months, your bones thin out, your muscles shrink, even though you're training hard. And then, after that, you don't go back to a hospital bed, you drop into Mars's gravity, about 0.38 G. That's roughly a third of Earth gravity. So yes, everything weighs less, but it's still a constant load, not a tiny one. Your suit, your tools, your backpack, the dust on your boots, all of that still has mass, and you still have to accelerate and decelerate it with every step, just in a lower gravity field. You're asking a deconditioned body to suddenly perform demanding physical tasks in a partial gravity it has never felt before. That's a recipe for fatigue, clumsiness, and injury right when you least afford it. And it doesn't stop at bones and muscles. Microgravity messes with your fluids and your brain. On Earth, blood and other fluids are pulled downward by 1G. In space, that gradient vanishes, and fluids shift towards your head. Faces puff up, legs look thinner. That might look funny in photos, but internally it's a serious stress. One of the big problems is something called spaceflight associated neuroocular syndrome, SANS. The increased pressure and fluid around the head can change the shape of the eyeball and affect the optic nerve. Astronauts have returned from long missions with measurable changes in vision, sometimes needing new glasses, sometimes with more worrying signs in the back of the eye. The brain doesn't get a free pass either. Imaging studies show that the structure and connectivity of the brain can change after long exposure to microgravity. White matter pathways shift. Some regions gain or lose volume. Blood flow patterns change, and there are signs that the risk of blood clots goes up. Put simply, the system that coordinates your movement, balance, decision-making, and fine motor control is being rewired by an environment it never evolved for. You're expecting peak mental performance from a crew whose nervous systems are being physically altered over months. At the same time, they're under constant stress and sleep disruption. Add on top of that the cardiovascular system. Without gravity pulling blood down, the heart doesn't have to work as hard to push it back up. Over time, the heart can get slightly smaller and less efficient for 1G conditions. The reflexes that help you avoid fainting when you stand up on Earth can weaken. When astronauts return, some of them struggle with standing and walking at first because their body isn't ready for a full-strength gravity field. Now apply that to Mars. After months in microgravity, you slam into 0.38 G, step out, and you're expected to not faint, not stumble, not misjudge your movements in a dangerous environment. The obvious question is, how long does it take to recover from all of this, and can you just fix it with rehab when you get home? The answer is uncomfortable. Even after coming back to Earth, bone and muscle recovery is slow. It can take many months, even a year or more for bone density to partially come back, and sometimes it never fully returns to pre-flight levels. Some astronauts, by bone density measurements, effectively come back with older bones than their actual age suggests. Muscles can be rebuilt with training, but that takes disciplined rehab and time in a safe environment. On a Mars mission, you don't get to wait for recovery before doing hard work. Your lowest physical condition is not at the end in a hospital, it's right in the middle of the mission. Landing and early surface operations hit you when your bones are weaker, your muscles are reduced, your cardiovascular reflexes are rusty, and your brain and eyes may have changed. You have to operate machinery, build and maintain habitats, fix problems, and then after months more of partial gravity and stress, you have to launch back off Mars and endure another long trip in microgravity, then survive re-entry into 1G. So now stack it up. Radiation is raising your lifetime cancer risk and maybe cutting into your cognitive performance. Microgravity is weakening your skeleton, shrinking your muscles, distorting your vision, and rewiring your brain and blood flow. You're asking a small group of people to do the hardest work of their lives in the worst physical state their bodies have ever been in, far away from any real medical help. That leads straight into the next problem. Even if you accept that your body will be battered and degraded, you still have to keep that body alive with air, water, and food inside a sealed system that cannot fail. If your own biology is struggling, what happens when the machines that are acting as your artificial planet have to run perfectly for years with no resupply and no backup Earth right next door? How do you keep humans alive for years when you've taken away the one system that has always done that job for free, Earth? The moment you leave this planet, you're not just flying a rocket, you're running a tiny, fragile copy of Earth's life support system inside a metal shell. And if any part of it stops, you don't get a second chance. Start with air, the thing you never think about because you've never had to. A typical person needs on the order of 1 kilogram of oxygen per day just to breathe, plus a system to remove carbon dioxide before it builds up to toxic levels. For a crew of 4 over 900 days, you're already into thousands of kilograms of oxygen demand, and that's without any margin. You can't just load all of that as tanks of gas or liquid and call it done, because the mass and volume explode. So you need regenerative life support, machines that take exhaled CO2, water, and waste and turn them back into breathable oxygen with very high efficiency. That means CO2 scrubbers, chemical loops, electrolysis units that split water into hydrogen and oxygen, and possibly systems that react that hydrogen with CO2 to recover more water. Every one of those systems has filters, Pumps, valves, seals, electronics. They have to run almost non-stop for years, with uptime close to 100%. On the International Space Station, similar systems already exist, but they get regular maintenance, and if something breaks badly, you can ship up replacements. On a Mars mission, you can't treat these as just more hardware. They are the lungs of the spacecraft. A glitch in a fan or a stuck valve can go from annoying to you have hours to fix this or you all choke very fast. Now look at water. On Earth, you open a tab and don't think twice. In space, every liter is a liability on the launch pad and a lifeline in transit. Say you're very conservative on a Mars mission and you allow each astronaut 3 to 5 liters of water per day, around 0.8 to 1.3 gallons for drinking and minimal hygiene. For a 900-day mission with 4 people, if you carried all of that fresh, you're in the range of tens of thousands of liters. That's tens of tons of water mass. Lifting that much weight out of Earth's gravity is brutally expensive and makes your rocket problems far worse. That's why current systems, like on the ISS, recycle roughly 90% or more of water. They reclaim moisture from breath, sweat, urine, and even humidity in the cabin and turn it back into drinkable water. On a Mars ship, you need that but more reliable, for longer with no resupply. If a pump in the recycler fails, or a filter gets clogged, or a sensor drifts and the system quietly produces contaminated water, you don't just call Houston and wait for a resupply capsule. You have whatever spare parts you packed before launch, and you have to diagnose and fix it yourself while rationing the few liters you have left. Water is too heavy to bring in unlimited quantities and too critical to lose for more than a day. Food looks simpler at first, but the numbers bite there too. A human doing real work in a stressful environment might need around 2,500 kilocalories per day. For 4 people over 2.5 to 3 years, you quickly hit something like 10 million kilocalories total. You can compress that into dehydrated meals, energy-dense foods, and vacuum-packed rations, but you're still talking about several tons of food. Every kilogram of that has to be lifted from Earth or pre-positioned at Mars. Food isn't just mass, it's morale. Eating the same few things again and again for hundreds of days in a metal tube has a real psychological impact. People talk about space farming, growing plants in controlled environments to turn CO2 into oxygen and biomass into food, closing the loop. That's attractive because plants could help with air recycling and give fresh food. But we don't yet have any multi-year, fully closed bioregenerative life support systems that have been tested in actual space conditions, with real crews depending on them at Mars durations. On a Mars mission, you don't want your life support hanging on an experiment that might get mold, past outbreaks, or unexpected failures at month 18. Tie this together and you see the core problem. Every life support function, air, water, food, temperature control, pressure control, has to work almost flawlessly all the time. On the ISS, if a key component of the water recycling system fails, you can get more water or replacement hardware in a cargo ship like Dragon or Cygnus in weeks. Even that situation is treated as serious. On a Mars ship, the nearest spare part is tens of millions of kilometers away, and nothing you launch later can catch up with you once you're on your transfer orbit. That means every major subsystem has to hit reliability levels equal to or better than commercial aviation, but in an environment that is far harsher. Airliners don't deal with vacuum outside the hull. They don't sit in a radiation field for years. And if something truly catastrophic happens, there is at least some chance of an emergency landing. In deep space, a single leak that goes unnoticed, a hairline crack in a tank, a connector that slowly corrodes, can escalate into a full loss of atmosphere or water with no rollback. Every kilogram of backup hardware you bring to protect against that loops you back into the mass and fuel nightmare from the rocket equation. So at this point, your crew is living inside a sealed, artificial ecosystem where one bad pump, one glitchy sensor, or one misrouted hose could be fatal. And they have to maintain it themselves, while under radiation, with weakened bodies, for nearly 1,000 days. That's the physical side, but there's another layer that's just as dangerous, and it doesn't show up in engineering diagrams. What happens to a small group of humans when you lock them together for years, cut off real-time contact with everyone else, and surround them with the constant knowledge that there is no way out? How stable do you think your mind would stay if every day for almost 3 years you woke up, saw the same three faces, the same metal walls, heard the same fans and pumps, and knew that outside was nothing but vacuum and radiation? A realistic Mars mission profile is around 900 days away from Earth, roughly 7 to 10 months out, 12 to 18 months on Mars, and another 7 to 10 months back. That's 3 birthdays and 3 cycles of your friends' lives on Earth, all spent locked into one mission with no option to tap out. Day to day, that means you live in a cramped, noisy, artificially lit volume, maybe a few tens of cubic meters per person. There is no fresh air, only recycled atmosphere. There is no going outside without a suit. Even on Mars, outside means putting on a life support system, walking in reduced gravity on a toxic, freezing surface, and knowing that one tear in the suit fabric or one valve failure ends you in minutes. Every sound, every vibration, every alarm has weight because it might be the start of a real emergency. Your brain never fully relaxes, it just moves between kind of alert and very alert. That background tension stacks on top of monotony. The same corridors, the same workstations, the same exercise machines, the same packaged food. Variety comes in small doses. A new message from Earth, a small experiment, a change in routine. On Earth, if a job starts to grind you down, you can change locations, travel, or even quit. On a Mars mission, there is no quitting. You agreed to be there for the entire 900 days, and the ship does not care if you wake up one morning and decide you've had enough. So if your world shrinks down to a metal tube and a few people, at least you can stay connected with everyone back home through constant calls and messages, right? This is where the speed of light hits psychology as hard as it hits navigation. Between Earth and Mars, the communication delay ranges from about 4 minutes one way at the closest, up to roughly 24 minutes one way at the worst alignment. That means a simple, "How are you?" and "I'm okay" round trip can take anywhere from 8 minutes to almost an hour. That delay kills normal conversation. You can send video, audio, text, but you never get a live reaction. Jokes land late. Emotional support arrives after the moment has already passed. If you're stressed, angry, or scared, you can record a message, but you can't see someone's face react. You can't feel that back and forth that normally calms people down. Socially, you're not talking with Earth, you're talking at Earth, and Earth is talking back at a different time. Over months, that changes how you relate to people. Family and friends keep living in 1G, you're dealing with checklists, radiation, and hardware in a different time zone of reality. You watch life on Earth as a delayed stream, not as something you're part of. Inside the crew, the opposite happens. Your few crewmates become your entire immediate social universe. Their moods, habits, and quirks start to matter in a way that's hard to describe until you have no one else. Now connect that to conflict. On Earth, if you have a bad day with a coworker, you go home, you see other people, you reset. If a team is not functioning, management can reshuffle, add members, or remove someone from the project. On a Mars transit, your coworkers are also your roommates, mechanics, doctors, and emergency contacts. There's no home to go to that isn't full of the same people. There's no option to swap someone out because they're annoying or because the team dynamic is off. Small frictions that would be trivial on Earth can grow into real resentment. If two people stop trusting each other, that can infect how they cooperate on tasks, including mission-critical operations. Here's the dangerous part. There is no neutral outside authority right there with you. Mission control is far away, responding with a delay. There's no onboard HR department that can pull someone aside, give them time off, or physically separate hostile parties. The commander is part of the same pressure cooker as everyone else, also stressed, also tired. You need the team to be cohesive at precisely the time the environment is pushing every weakness and personality clash to the surface. And that's just the baseline, the nothing catastrophic has happened yet mode. What happens when a real crisis hits a crew that is already under chronic psychological load? A major system fails and you have minutes to respond, or someone has a serious medical emergency, or in the worst case, there is a death on board or on the Martian surface. On Earth, even in tough environments, there is always the underlying knowledge that rescue is at least theoretically possible. On a Mars mission, the crew knows there is no rescue ship coming. There is no medevac. If something horrible happens, they still have to get up the next day, work the checklists, maintain the systems, and continue the mission because stopping is not an option. The psychological shock lands on people whose coping resources are already worn down by isolation, monotony, physical discomfort, and the constant awareness of risk. We study parts of this using analogs, isolation experiments in places like Antarctica, underwater habitats, or sealed mock bases. These teach us a lot about group dynamics, stress, and confinement, but none of those analogs perfectly match a Mars mission. They don't combine multi-year duration, total lack of real-time contact, deep space radiation, microgravity, and the knowledge that beyond a few centimeters of metal is vacuum. So at this point, you have a crew whose bodies are weakened, whose radiation risk is climbing, whose minds are under continuous strain, and whose only lifeline is a set of machines that must not fail. And they still haven't even touched the thing that will try to kill them next, the planet itself. Because Mars is not a friendly landing zone waiting to welcome you. It's an almost airless world where the atmosphere is too thin to help you land gently, but thick enough to burn you up if you get the entry wrong. How do you land and live on a planet that technically has an atmosphere, but not one that actually helps you stay alive? Mars looks like it has air and all the nice renderings, but the numbers say you are basically dealing with a vacuum in denial. Start with the pressure. At the surface of Mars, the average pressure is around 610 pascals. Earth sea level pressure is about 101,325 pascals. That means Mars is sitting at roughly 0.6% of Earth's air pressure. In PSI, you're looking at something like 0.088 PSI on Mars versus about 14.7 PSI at sea level on Earth. That's not just tough mountain air. That is below something called the Armstrong limit, around 6,300 pascals. Below that, exposed bodily fluids, like the water in your saliva and the moisture on your eyes, can start to boil at normal body temperature. So all those casual step outside and take your helmet off ideas don't just fail, they kill you in seconds. Your blood won't explode out of your veins Hollywood style, but you will black out quickly, your lungs will be damaged, and if you're not repressurized almost immediately, you die. There is no scenario where you stand on Mars, breathe a bit of the air, and walk it off. You need a full pressure suit every time you go outside, and your habitats have to hold almost the same internal pressure that you're used to on Earth against an outside that is barely above vacuum. If the atmosphere can't keep you alive, maybe it can at least be useful as a break, right? After all, Earth's thick air helps you land everything from capsules to airliners. Here's the problem. On Mars, the air is too thin to do the job for the kind of mass a human mission needs. On Earth, re-entry vehicles and parachutes can dump huge amounts of speed and energy into the atmosphere. The drag is strong because the air is dense. Parachutes can be relatively compact and still generate massive braking force. On Mars, with less than 1% of Earth's surface pressure, the air barely grabs you. For small probes and rovers that weigh hundreds of kilograms up to a ton or so, like Curiosity or Perseverance, you can combine aeroshells, parachutes, and retro rockets right near the end to make it work. Even that was hard. Those missions used complex sky crane systems to lower the rover down. Now, scale that up to a crewed lander plus habitat, potentially tens of tons total. Parachutes alone simply cannot slow that kind of mass enough in that thin air before you hit the ground. The atmosphere is in this annoying zone where it's strong enough to heat you up violently during entry, but too weak to give you a clean, parachute-only landing for heavy payloads. So you end up with hybrid solutions. Heat shield and aeroshell to survive the first part of entry, maybe a supersonic or hypersonic parachute to shave off some speed, then for the last part, big rocket engines firing downward to bleed off the rest and gently set you down. That supersonic retro propulsion is hard engineering, and we have not yet done it on Mars at the scale you'd need for a full human lander. It's not just add more engines, it's making sure those engines and their exhaust don't destabilize the vehicle in thin air, don't kick up so much dust that sensors are blinded, and don't blast craters under the landing legs. All of that is wrapped inside the nastiest few minutes of the entire mission, the hypersonic entry. When you arrive at Mars, you slam into the upper atmosphere at around 5 to 7 kilometers per second, roughly 11,000 to 15,000 miles per hour. That is hypersonic flight in a very unforgiving environment. Your heat shield has to take massive thermal loads and mechanical stress. The angle at which you enter the atmosphere has to be in a narrow corridor. Too steep, and the deceleration and heating spike, and you risk burning up or smashing into the ground too fast. Too shallow, and the thin air doesn't slow you enough. You can skip out and back into space, with no fuel to try again. There is no go around like in aviation. There is no second pass. You get one shot at this entry. The guidance system has to keep the craft at the right angle, the structure has to survive the heating, the parachutes have to deploy at the right speed and altitude, and the retro rockets have to light and throttle correctly in a low-density atmosphere. Any major failure in that chain turns into a crater or a lost vehicle. And remember, you can't fully rehearse this with humans. You test pieces, you test at smaller scales, but the first full-scale human lander will be pushing into a regime where experiments and the real mission are dangerously close. Suppose you somehow thread that needle. The heat shield works, the parachutes behave, the engines do their job, and you're standing on Mars in one piece. Now you have to deal with the part that looks harmless in photos, but is not. The dust. A lot of people imagine Martian storms as huge, violent wind events that can flip vehicles over. The reality is a bit different. Because the air is so thin, even high wind speeds don't produce the same force you'd feel in a hurricane on Earth. A 100 km/h wind on Mars, around 60 miles per hour, hits you more like a gentle breeze in terms of push on your body. The danger is in what that thin air carries. The dust on Mars is extremely fine, like talc, and it can get electrostatically charged and cling to surfaces. When storms kick up, that dust can go high into the atmosphere and wrap the entire planet in a hazy blanket for weeks. That cuts down sunlight, which is bad news for solar panels. Your power generation can drop at the exact time you need heat and systems running steadily. If you rely heavily on solar, a long global storm can put you into a serious energy deficit unless you have huge storage or backup nuclear power. Dust also gets into everything mechanical. Joints, seals, hinges, radiators, air intakes, suit bearings. It is abrasive, so it slowly wears down surfaces. It can block radiators and reduce your ability to dump waste heat, which matters a lot in a closed habitat. It can contaminate airlocks, get trapped inside, and interfere not just with machinery, but with health, especially since Martian soil also contains chemically reactive compounds like perchlorates. Every time you go outside, you risk bringing that stuff back in on your suit, and every moving part on your lander and rovers is slowly grinding against it. So the atmosphere on Mars fails you in every major role. It's not thick enough to breathe, not thick enough to land on easily, but just thick enough to burn your ship on the way in and to move dust into every crack of your equipment. You can't live in it, you can't land purely with it, and you can't ignore the damage it causes. And the punchline is, this is still the buffer zone around the planet. Once you're down, you're not dealing with a friendly new home. You're standing on the world that is cold enough to freeze you solid, with soil that can poison you, gravity that's wrong for your body, and radiation still pouring in from above. Solving the atmosphere problem only earns you the right to face the surface itself, which is its own list of reasons Mars is less a destination and more a hostile lab test for human survival. Mars looks calm in photos. Clear sky, dusty rocks, maybe a sunrise. On the surface, it is a place that quietly tries to kill you with temperature, chemistry, gravity, and radiation all at the same time every single day. Start with the cold. Mars is not winter in Siberia cold. It's a different category. The average temperature is around minus 63 degrees Celsius, about minus 81 degrees Fahrenheit. That's the average. At night, especially at mid-latitudes where you'd probably land, temperatures can drop below minus 100 Celsius, around minus 148 Fahrenheit. Exposed skin doesn't just get chilly there, it shuts down fast. Metal becomes brittle, plastics stiffen, batteries lose performance. That means every single cubic meter of your habitat has to be insulated and heated constantly. The walls, the floors, the airlocks, every pipe that carries water or air, everything has to be kept above freezing, or it will crack, leak, and fail. You're not heating one house with a backup power grid behind it. You're heating a small base in a place where outside air is almost vacuum, and the ground is sucking heat out of you all the time. Now think about your suit. An EVA suit on Mars is not a thick jacket with some heaters. It's a walking spacecraft. It has to provide pressure, oxygen, CO2 removal, communication, and thermal control while you move, bend, lift, and kneel on sharp rocks. It has to keep liquid water inside tubes from freezing solid when the outside environment is below -100 Celsius. And it has to do that for hours at a time, day after day, as pumps, valves, and seals age. One minor failure in that system in those conditions can go from annoying to lethal very quickly. Temperature is only one threat. The ground itself is a chemical problem. Martian regolith, the dusty, rocky material on the surface, isn't just inert dirt. Measurements from landers and rovers show it contains perchlorates, reactive chlorine compounds. These are toxic to humans in significant doses and can interfere with thyroid function and other parts of your biochemistry. So every time you track dust into the habitat, every time it sticks to a suit seal or a glove, you're not just dealing with a cleanliness issue, you're bringing in a low-level chemical hazard. Now add that to the dream of growing food in Martian soil. If you want to plant anything directly in that regolith, you have to either remove or neutralize those perchlorates and maybe other toxic components. That means washing, heating, or chemically treating tons of soil in a place where water and energy are limited and every system is already working flat out. You can shield plants from the dust and use hydroponics or imported soil mixes, but then your farming is basically a high-tech chemistry and engineering project, not a simple greenhouse. Even if you handle the chemistry, gravity on Mars is its own question mark. The surface gravity is about 0.38 g, roughly one-third of Earth's. At first glance, that sounds fun. You can jump higher, carry more, feel lighter. But your body is not optimized for that. Human bones, muscles, heart, and blood vessels evolved in 1G. We know what happens in 1G, we know what happens in almost 0G from the ISS, and it isn't good. But for long-term life at 0.38G, we basically have no data. That's the scary part. We don't know if 0.38G is enough to stop the bone loss, muscle atrophy, and cardiovascular deconditioning you see in microgravity. It might slow it down, but not stop it. You could end up in a worst of both worlds situation, where gravity is high enough to make every movement cost energy, but too low to tell your body keep the skeleton and muscles in full working order. Over years, that can mean slow, progressive loss of capability, while the workload on the surface is going up. And over all of this, there's the radiation that never really goes away. Earth has a strong global magnetic field, a magnetosphere, that deflects many charged particles from the sun and from space. Mars does not. It has patches of crustal magnetism in some regions, but no big global shield. Charged particles slam into the atmosphere and the ground more directly, contributing to that higher radiation dose we already talked about. Even inside a well-designed habitat, buried partially under regolith or covered with shielding, you're still taking more radiation than you would on Earth. On the moon, you might get slightly different profiles, but moon missions are shorter and closer. On Mars, the whole point is to stay longer, to build and explore, and that longer exposure time means your shielding needs are higher in practice because you're integrating that dose across years, not weeks. So the surface environment combines all the worst factors: deep cold that punishes every mechanical system, dust and soil that introduce chemical and mechanical hazards, gravity that might quietly degrade your body over the long term, and radiation that keeps hitting you from above because there is no magnetic umbrella to hide under. You don't get a break from any of these. You're either fighting them with hardware, procedures, and careful planning, or they erode your safety margins day after day. And here's the part that makes it even more fragile. While you're trying to function in that hostile environment, your entire medical system is whatever you can fit into a small room and a few boxes. So what happens when you break a bone in that weaker skeleton, or your vision shifts, or someone has appendicitis and the nearest real hospital is tens of millions of kilometers away? How do you run serious medicine when your entire healthcare system is one room, a few cabinets, and a handful of people who are already exhausted just from staying alive? On Mars, the medical bay isn't a sci-fi hospital with holograms and endless gear. It's a cramped compartment with basic equipment and maybe one crew member who's a doctor or paramedic, plus a backup with some extra training. That tiny setup has to cover fractures, burns, infections, dental emergencies, mental breakdowns, and long-term radiation and bone problems for years. Think through the range. Someone trips in a suit, hits a rock, and fractures a weak leg bone that's already lost density from months in 0G and then 0.38G. Someone develops a serious tooth problem, and without treatment, that pain can wreck sleep and performance. Someone gets a deep cut while fixing hardware in a dusty environment full of perchlorates and unknown microbes. Someone else starts showing serious anxiety, insomnia, or depression from stress and isolation. On Earth, you'd split these across specialists: orthopedics, dentistry, infectious disease, psychiatry. On Mars, you have one small room, a basic set of tools, and a crew medic who might be doing surgery one day and fixing an air filter the next. Even the baseline assumptions about illness are shaky because spaceflight changes how your body fights disease. Microgravity and radiation affect the immune system. Some immune cells don't react the same way they do on Earth, and the balance of different cell types shifts. Studies show that latent viruses, like herpes family viruses, can reactivate more often in astronauts. Some microbes exposed to space conditions have shown changes in virulence or resistance. So a cut, a chest infection, or a stomach bug that would be routine on Earth might behave differently out there. That means protocols written for Earth, where gravity, atmosphere, and immune response are all normal, might not map cleanly to Mars. Antibiotic choices, dosing, healing times, all of that becomes fuzzier. You can't easily run full lab tests, culture samples, or send them to a bigger facility. You can't call a specialist and say, "Come take a look at this." You can send data and images back to Earth, but with a delay of minutes each way, and you're relying on whatever diagnostics you manage to pack into the ship. Now push it to the ugly scenario: major surgery. On Earth, a bad accident might send you to an operating room with a full team: surgeon, anesthesiologist, nurses, techs, imaging, blood bank, intensive care. On Mars, if someone needs their appendix out or has internal bleeding from trauma or a serious abdominal problem, who does the operation? Most likely, your surgeon is the crew's medical officer, who may be a very capable doctor, but is still just one person working with an assistant who is not a trained surgical nurse in a habitat that was never designed as a perfect operating theater. Gravity at 0.38G changes some of the basics. Fluids don't pool exactly like they do at 1G. Blood, irrigation fluid, and tissue behave differently. You can't rely on decades of experience cutting people open and keeping them stable in Martian gravity. Keeping the field clean and sterile is harder in a dusty environment. Airflow in a small, closed habitat can move particles around in ways you don't fully control. You don't want Martian dust or habitat contaminants anywhere near an open wound. On top of that, your surgeon is not walking into the OR fresh. They are living under the same chronic stress, sleep disruption, radiation exposure, and physical deconditioning as everyone else. Their hands might be a bit shakier from fatigue, their concentration pulled in different directions, but there is no one else to call. If they don't operate, the patient probably dies. If they do operate and something goes wrong, there is no higher level of care to transfer the patient to. The margin for error is almost zero. Then there's the thing people on Earth lean on without thinking: evacuation. In normal life, even in remote environments, the plan is always, if this gets really bad, we'll evacuate. a helicopter, a plane, a long ambulance ride, but still, you can get to a bigger hospital. On Mars, that option simply doesn't exist. Evacuation means staying exactly where you are. The ship isn't fueled and ready to launch at a moment's notice, and even if it were, the transfer windows and travel time make rapid return impossible. So you're mixing several things that are each dangerous on their own. High-risk physical work in suits and vehicles, a hostile environment that punishes small errors, bodies weakened by radiation and low gravity, immune systems that don't behave normally, and the medical setup that is tiny, limited, and trapped in place. Then you remove the one safety net modern societies rely on: access to advanced hospitals and specialists. If a condition progresses in an unexpected way, if a fracture heals badly, if a mental health crisis escalates, there is no higher level of care beyond what you already brought with you. This is where the idea of acceptable risk gets very real. You're not just asking, can we land a rocket? You're asking, are we willing to accept that if someone on this mission gets a condition that would be survivable on Earth, they might die on Mars because the tools and help just aren't there? And you have to ask that knowing that the same crew you're putting in that position is also your only path to building anything lasting on the surface. And here's the kicker. Even if you accept that brutal medical risk, the mission doesn't end with surviving Mars. At some point, you have to leave. That means your entire future depends on hardware that was either sitting on the planet for years before you arrived, or fuel that was supposed to be manufactured automatically from Martian resources. So the next question is even sharper. After everything you've gone through, how sure are you that your ride home is real, fueled, and actually able to light up when it's time to go? How confident would you feel stepping on Mars if, deep down, you knew your ride home was something you launched years ago and just hoped was still alive? Getting to Mars is hard. Staying alive on Mars is harder, but leaving Mars and making it all the way back to Earth might actually be the most fragile part of the whole mission. A realistic mission plan has a harsh rule. You have to set up the way back before the crew ever commits to landing. That usually means one of two things. Either you pre-position a fully fueled descent vehicle on the surface waiting for them, or you land an ISRU plant years in advance, a system that turns Martian CO2 and buried water ice into methane and oxygen, and fills empty tanks over time. Both options sound smart on paper, but they come with the same nightmare. What if that hardware fails quietly and nobody notices until it's too late? Picture the sequence. Before any humans go, you launch an uncrewed mission. It drops an ascent rocket onto Mars, or an ISRU unit that starts sucking in CO2 and digging for ice. Telemetry looks fine. Sensors say the tanks are filling. The systems are green. Years later, the crew leaves Earth, spends months in deep space, survives the transfer, the entry, the landing, the surface environment, and only then do they physically inspect their ride home. If the tanks are not full, or the ISRU plant clogged up, or something cracked in the cold, they're already there. They're committed. You can build in checks and redundancy, but you cannot remove the basic risk. You are trusting that a machine sitting alone on Mars for years will do exactly what you expect, with no human eyes on it and no repair team on site. Even if everything worked, getting off Mars isn't a casual hop. The escape velocity, the speed you need to break free from Mars's gravity, is about 5.0 kilometers per second, around 11,200 miles per hour. That's lower than Earth's, but it still demands a serious rocket, not a small hopper. That ascent vehicle has to carry enough propellant and thrust to lift a crew cabin, their suits, maybe some samples, and match up with an orbiting target. It's its own mission, stacked on top of the larger mission. Now think about what that rocket goes through while it waits. It sits on Mars for months or years, depending on the architecture, exposed to dust storms, extreme temperature swings from day to night, and radiation that slowly degrades materials and electronics. Seals can age, valves can seize, propellant can stratify or freeze in lines if thermal control fails. Wiring can get damaged by tiny faults that only show up when you finally ask for full power. You can't roll it back into a hangar and service it. You can't swap out engines. When departure day comes, that vehicle has to light on command and perform within tight margins. If it doesn't, there is no backup launch pad across town. And remember, the ascent itself is just the first step in coming home. In many mission plans, the ascent vehicle is not the same spacecraft that takes you back to Earth. It gets you into Mars orbit, where you have to rendezvous with an Earth return vehicle that was either parked there ahead of time or arrived separately. That means precise navigation, timing, and engine performance at an interplanetary scale. Rendezvous in orbit around Earth is already a delicate operation, and we've practiced that for decades. Around Mars, you add signal delays, fewer chances to test the full chain in advance, and the fact that if you miss the window, you don't have many options. If the ascent vehicle underperforms and ends up in the wrong orbit, or if a guidance error leaves you slightly off, you might not have the propellant to correct it. If you don't get close enough to dock with the Earth return ship, you can't just call for a rescue tug. The crew could end up in a useless orbit with no reachable backup, watching the one spacecraft that could take them home pass out of practical reach. Say you nail that. You launch cleanly from Mars, rendezvous perfectly, and transfer the crew into the Earth return vehicle. You still have months of deep space travel ahead, with all the same radiation and life support risks you faced on the way out, plus accumulated wear on every system. The crew by now has gone through extended microgravity on the outbound trip, months of 0.38 G on Mars, and now more microgravity on the way home. Bone density is down, muscles are reduced, cardiovascular reflexes are dulled, and their nervous systems have been under stress for years. Then, at the very end, you hit the final high-risk maneuver, re-entry to Earth. The capsule has to survive intense heating and high deceleration, maybe several Gs of load depending on the profile. For a body that's been living with lower gravity and deconditioning, those G-forces hit harder. Blood shifts, hearts strain, bones and muscles are asked to endure a stress they haven't felt in years. At the same moment, the heat shield, parachutes, retro rockets, and landing systems have to work perfectly, even though they too have been sitting in space for years, dealing with temperature cycles, radiation, and maybe micrometeoroid hits. There are no fresh backups for any of that. You can't swap a heat shield in orbit after 2.5 years. You can overbuild and test, but once the mission flies, the hardware just ages. By the time the crew hits the atmosphere back at Earth, they are relying on systems that have been in the harshest environment we know for longer than almost any human-rated spacecraft has ever operated continuously. So when you zoom out, coming home from Mars isn't the simple reverse of going there. It's a chain of conditional bets. You're betting that uncrewed hardware landed years in advance will be healthy and full of fuel. You're betting that a rocket that's been sitting in Martian dust and cold will light and fly on schedule. You're betting that you'll hit a precise rendezvous in Mars orbit with no rescue if you miss. And you're betting that, after all of that, a long-aged return vehicle will protect a weakened crew through one last violent plunge into 1G. And all of this has to be built, launched, coordinated, and operated on top of the rockets, habitats, landers, ISRU plants, and life support systems we already talked about. None of that comes cheap, and none of it fits into a small, neat budget. So the next question isn't just can we do it, it's can we build and launch this much hardware, on time, over and over with the industry we have right now. The uncomfortable answer is that a true Mars program doesn't look like a big mission. It looks like an entirely new layer of industrial infrastructure we don't really have yet. Start with the raw scale. Even very optimistic Mars architectures, the ones that assume heavy lift rockets that work well and can be reflown, still end up needing dozens of big launches for a single full campaign. You're not just lifting one cruise ship, you're also sending cargo landers, surface habitats, rovers, power systems, ascent vehicles, propellant depots, maybe an orbital return vehicle, and all the propellant to feed them, sometimes in multiple phases over many years. Each heavy lifts rocket might be able to put, say, tens of tons into low Earth orbit, maybe more in the best cases. But your total mission mass into low Earth orbit, once you add everything, easily reaches into the hundreds or even thousands of tons for a robust, safer architecture. Right now, global launch capacity in that hundreds of tons to low Earth orbit per year range is only just starting to appear. To support regular, repeated Mars missions, not just a one-off stunt, you'd need something more like an interplanetary cargo pipeline, a launch cadence where throwing 100 or 200 tons to orbit is routine, not headline news. That directly ties into money. None of this is cheap. A single multi-year Mars mission with all the development, testing, ground support, and actual launches can easily end up in the tens of billions of dollars. And depending on how cautious and redundant you want to be, you can climb toward the hundreds of billions. That's not just one country's space budget for a year. That's many years of serious spending. That pile of money sits next to everything else people care about: climate mitigation, healthcare, education, infrastructure, defense, disaster response. Voters feel potholes in the road and hospital wait times in their daily lives. They do not directly feel the lack of a Mars mission. So every time budgets are cut, priorities shift, or a crisis hits, long-term space projects are easy targets. And a Mars mission is not a 3-year sprint. It's a decade-plus grind. You need stable funding through design, prototyping, testing, the uncrewed precursor missions, then the crewed mission itself. History is not kind here. Even relatively modest long-term programs struggle to hold attention for 10 or 15 years. Programs get restructured, renamed, delayed, or canceled. Hardware that was almost ready ends up in museums. To get humans to Mars and back safely, you need a rare alignment: high funding over many budget cycles, without someone deciding that the money is better spent on problems closer to home. Then there's the supply chain. This isn't consumer electronics. High reliability space hardware isn't pumped out of factories in months. Components are specialized, vendors are limited, and qualification testing takes time. A single valve, sensor, or computer might have a lead time measured in years, not weeks. Every flight item has to be tested, sometimes batch tested, sometimes individually, and then integrated into larger systems that also need full test campaigns. A Mars campaign squeezes all of that into a tightly choreographed schedule because of those 26-month launch windows. If one critical part is delayed, maybe a key engine component or a life support module, you can't just roll the launch back by a couple of weeks and still hit the ideal transfer window. Slip long enough and you miss the window entirely, which pushes not by weeks, but by more than 2 years. That delay ripples through everything: hardware waiting in storage, teams losing momentum, contracts needing extensions, and budgets stretching out. The mission timeline becomes fragile, not just because rockets can fail, but because the industrial pipeline feeding them is slow and rigid. On top of that, Mars missions are a nightmare to insure in any normal economic sense. You can insure a satellite. If it fails, the payout covers the hardware and the launch fee. You can insure a ship or a building, but a human Mars mission is not just hardware. If a crew is lost, you're dealing with human lives, worldwide attention, and reputational damage to agencies and companies that can last decades. There is no insurance policy that meaningfully covers that. That reality drives behavior. Governments and companies become very risk-averse because a single high-profile catastrophe can shut down not just one mission, but the entire idea of human deep space exploration for a generation. At the same time, Mars missions are inherently high risk. You can't make them as safe as commercial air travel, not with current technology. So you end up in a contradictory space. Everyone wants the risk to be low enough to be survivable, but the physics and biology keep pushing it higher than people are comfortable with. Put it all together and the scale problem is brutal. You need an industrial base that can throw huge masses into space regularly, a system willing to bankroll that for many years, a supply chain that can deliver ultra-reliable parts on tight, unforgiving schedules, and a risk tolerance that accepts that things can still go very wrong in public. Without all of those aligned, the Mars plan doesn't even get to the launch pad. And even if you somehow line them up, you still face one more layer. Every single system you build has to work for hours or days, but for 1,000 days or more, in deep space, with humans depending on it for every second of uptime. That's the bar for a Mars mission. It's not enough to launch once and work for a few hours like Apollo. You need a whole stack of life-critical systems that don't get a proper workshop, don't get a reset, and don't get a rescue. A lot of people point at satellites and probes and say, look, they last for years. True, many of them do, but most of those machines have an easier job. If a deep space probe's camera dies early, it's sad, but nobody suffocates. If a weather satellite locks up, you lose data, not a crew. A human Mars mission is different. Life support, thermal control, power, guidance, propulsion, comms, environmental monitoring, they all have to stay up for 2 to 3 years straight, and most of them are single points of failure at some level. Think about simple hardware like pumps, valves, filters, computers, batteries. In your house, if a pump fails, you call a technician. In your car, if a valve sticks, you pull over. On a Mars ship, if the wrong pump dies, maybe the coolant loop for your electronics or the water recycler feed, you can't pull over. If a filter clogs and you don't have a spare, the system it protects can get contaminated and take down something else. A failing battery cell can drag down a whole power bank. One fault at the wrong time cascades into a chain of failures that multiplies the risk everywhere else. So you try to protect yourself the obvious way. You add backups. Redundancy is the standard answer, but it comes with its own trap. Say you add a second pump, a second computer, an extra O2 generator. On paper, that sounds great. If one fails, you switch to the other. But every backup is another device that can fail, another piece of software that has to be tested, another configuration that can be wrong, another interface that can misbehave when things get weird. Interactions between systems grow fast. The result is that your spacecraft doesn't just get a little bit bigger, it becomes far more complex. Apollo hardware was already intricate, and that was for missions that lasted days and never left Earth's neighborhood. A Mars vehicle with full redundancy for life support, power, propulsion, and navigation is in a different league. The number of combinations you have to test explodes. You're not just checking, does this pump run? You're checking, does this pump hand over correctly to the backup during a fault while the computer's rebooting and the power bus is under load? And you need to know that works every time, because you won't get to fix it later if it doesn't. Add a space weather to the mix. Radiation doesn't care that your electronics pass tests in a clean lab. High-energy particles can flip bits in memory, corrupt instructions, and cause sensors to glitch. Over time, radiation also physically degrades components, changing how they behave. Deep space missions already use hardened electronics and error-correcting software just to keep uncrewed probes running. For human systems, your target reliability goes way up. You're aiming not for pretty good uptime, but for something like 5, 6, or 7 nines of reliability, so 99.999% and beyond across mission-critical subsystems. That sounds impressive, but now think about what that means over thousands of hours, under constant radiation, in a vacuum, with thermal cycles from sunlight to shadow, and limited physical access for repairs. The margin shrinks to almost nothing. When a cosmic ray flips a bit in a control computer at the wrong moment, you can't afford that to cascade into a thruster firing wrong or a life support controller locking up. You try to fight that with layers of protection. Triple redundant computers voting on commands, watchdog timers, fail-safe modes that degrade gracefully instead of collapsing. But every layer adds more code, more logic, more potential bugs. The more you harden, the more complicated the full system becomes, and the harder it is to be sure you've tested every weird edge case that might appear after 600 or 800 days in deep space. And here's the catch you can't dodge. You will never run a full end-to-end dress rehearsal with humans for the whole mission. You can test pieces in vacuum chambers. You can run analog habitats in deserts or underwater. You can put segments of life support on the ISS. You can simulate operations in software and hardware-in-the-loop rigs. But you cannot take a fully loaded Mars ship, put a real crew in it, fly it on a 3-year fake mission, and then say, "Cool, now let's do the real one." The real one is the test. That means your first actual crewed Mars mission is, no matter how careful you are, an experiment. A high-stakes, massively engineered, heavily simulated experiment, but still an experiment. And experiments sometimes turn up failure modes nobody thought of in advance. Something in the interaction between hardware, software, human behavior, and the space environment will behave differently than the model said. On the ISS, you can usually fix or adapt. On the way to Mars, you might not get that chance. So step back and look at the stack. Every system has to work for years. Redundancy keeps you alive, but also multiplies complexity. Radiation is quietly attacking your electronics, and you will never truly know that the whole machine works as a unit until you put real people in it and commit them to a one-way path for months. This isn't the same engineering mindset as building a car or even an airliner. It's pushing into a reliability regime where the tolerable failure rate is close to zero in an environment designed to produce failures. And that leads straight into the hardest question people usually avoid saying out loud. If we know all this, if we know the risk can't be squeezed down to something comfortable, how many lives are we really prepared to spend to make Mars happen? Because at some point, the mission isn't just about engineering anymore. It's about ethics. When you strip away the hype, you hit a blunt question that doesn't fit into launch videos or press releases. How many people are you actually willing to lose for Mars? Exploration has never been safe. Early ocean voyages had ships vanish with all hands. Polar expeditions had whole teams freeze or starve. Back then, high death rates were expected, and the world barely knew the details. Today, every accident is live-streamed, replayed, dissected, and turned into headlines. Modern societies are much less willing to accept visible, preventable deaths, especially in big public programs that run on taxpayer money. If you tried to run Mars exploration with the same casualty rate as early polar exploration, where major expeditions sometimes lost half their people or more, the public would shut it down instantly. Even losing a single crew on a high-profile mission now creates a shockwave. Look at how much the Challenger and Columbia shuttle disasters changed space policy, and those were in low Earth orbit, with flight rates and experience on our side. A fatal Mars accident would be worse because everyone would know the crew died far away, with no rescue attempt possible, after billions were spent to send them there. That's the pressure leaders live under. They know one big public failure could freeze human deep space exploration for an entire generation. So they push space agencies and private companies hard in two directions at once. On one hand, make it safe. Make the chance of failure tiny. We can't afford a disaster. On the other hand, move fast, show results, hit ambitious timelines, justify the budget. Those demands clash. Pushing risk down means more testing, more redundancy, more time, more money. Pushing timelines means cutting corners, accepting unknowns, and flying earlier. Trying to do both at once is almost impossible without someone, somewhere, lying to themselves about how much risk is really left. Then there's the issue of consent. Yes, astronauts and future Mars crew members will be volunteers. They will sign up knowing this can kill them. But knowing has levels. You can explain launch risk, landing risk, suit failure risk. You can point to past accidents and probabilities. What you can't do is hand them precise numbers for things we've never done before, like living for years in deep space radiation, or spending a long stretch in 0.38 G, or being psychologically isolated for 900 days with no real-time contact. We don't actually know the lifetime cancer risk from a full Mars mission with current shielding levels. We don't really know the odds of permanent neurological changes from long-term radiation and altered blood flow in the brain. We don't know how partial gravity affects fertility, pregnancy, and long-term organ health, especially if people ever try to stay on Mars for decades. When you ask someone to sign up, you're asking them to accept not just high risk, but fuzzy, poorly constrained risk. Ethically, that's tricky. Informed consent means they understand what they're agreeing to, but part of the truth is we don't actually know how bad some of this could be. Layered onto that is a different kind of responsibility: planetary protection. You're not just moving people and gear, you're moving biology between worlds. If you send humans to Mars, you're sending Earth microbes no matter how careful you are. They're in your bodies, in your air systems, in tiny crevices of your hardware. You have to think about what that does to any possible native Martian environment, even if it's just microbial, and what it does to our ability to study it. Once you seed a site with Earth life, you may never again be sure if a sample contains Martian biology or contamination from your own systems. And the risk runs the other way too. If Mars has any form of life, even primitive microbes, you have to assume there's some non-zero chance that bringing samples back could introduce something harmful to Earth's biosphere. Maybe it's extremely unlikely that a Martian organism could infect Earth life or disrupt ecosystems, but extremely unlikely isn't the same as impossible, and you don't get to run that experiment twice. So you build in strict sample handling procedures, sealed containers, sterilization protocols, and quarantine plans for both material and people returning from Mars. All of that adds more mass, more complexity, and more cost. Secure sample containers are heavier. Quarantine modules need volume, life support, and shielding. Procedures for avoiding contamination slow down operations and add steps where things can fail. You might end up in a situation where the safest thing for Earth is to keep certain samples in orbit or on the moon, rather than bringing them straight down to the surface. That complicates the already complicated mission even further. So step back and see how these ethical constraints squeeze the mission from every side. You have to keep the visible body count as close to zero as possible in a mission profile where the true risk is absolutely not zero. You have to ask volunteers to accept unknown long-term damage with incomplete data. You have to avoid trashing another planet's potential biosphere while also protecting Earth's, which requires strict, expensive safeguards. And every time you add protection, you add hardware, mass, and cost, which loops back into the rocket equation and launch cadence and industry limits. In the end, Mars forces you into a corner. Either you accept the level of risk and uncertainty that modern societies are deeply uncomfortable with, or you slow down so much and build so conservatively that the mission starts to look impossible with current money and infrastructure. And behind all of this, there's a question we still can't answer clearly. Even if you somehow solve the tech and the ethics, is the human body even capable of living long-term in 0.38 G at all? Or are we trying to build a future on a planet that our biology simply cannot adapt to? You can engineer rockets and life support on paper, but what happens if the basic gravity of the planet is wrong for your species and you only find that out after you've moved people there? Right now, almost everything we know about how the human body responds to gravity comes from 2 points on the graph, 0G in space and 1G on Earth. Mars sits in the middle at about 0.38 G, and we've basically never tested that with humans for any serious length of time. At 0G, we already know the story, and it's not good. Astronauts lose around 1 to 1.5% of bone mineral density per month in key weight-bearing areas. Muscles, especially in the legs and core, shrink and weaken even with aggressive exercise. The cardiovascular system deconditions. Reflexes that keep blood from pooling in the wrong places get weaker, and some people struggle to stand up when they come back to 1G. There are changes in the immune system, in fluid distribution, even in how the brain is wired. In other words, microgravity is not neutral. It pushes the human body downhill in multiple ways. At 1G, your body works. It's what everything in you has been tuned to through millions of years. Bone, muscle, heart, and brain are all optimized around constantly resisting that pull. We have massive medical data sets for people living their whole lives at 1G. We know what normal looks like. For 0.38 G, we have almost nothing. No long-duration human stays in a partial gravity field, no multi-year missions, no big statistics. Some animal experiments and short-term studies hint that partial gravity helps compared to 0G, but helps compared to terrible is not the same as good enough to live on for decades. That leads to a simple but nasty question. Could Mars gravity be the worst of both worlds? Not low enough to protect you from microgravity damage, but not high enough to feel easy. If 0.38 G is too weak to fully maintain bone and muscle, your body might still keep shedding density and strength, just more slowly than in 0G. But you still have to work. You still have to walk, carry gear, dig, climb, and build. Every movement costs energy. Suits and tools still have mass even if they weigh less. So you might end up in a situation where settlers feel a constant low-level fatigue. They get tired faster, they need longer to recover, but the long-term trend is still downward. Bone loss continues, muscle loss continues, and cardiovascular capacity lags, while the tasks they're performing get more demanding as the base grows. Over years, that means the average person on Mars could slowly lose physical capability even while the environment demands more strength, balance, and stamina just to keep up. That is a very bad feedback loop for survival, especially if medical care and rehab options are limited. Now, push beyond short-term missions and ask a heavier question. What happens if you try to have not just visitors, but generations? If the goal is a settlement, not just flags and a few footprints, you eventually have to think about pregnancy, fetal development, childhood growth, and lifetime health in that 0.38G and high radiation environment. Right now, we know almost nothing about how that plays out. We don't even have solid answers for long-term adult health in reduced gravity, never mind embryos and children. Reduced gravity could alter how organs form, how bones mineralize, how the heart and blood vessels develop, and how the nervous system wires itself. Add radiation, and you're stacking increased mutation risk and potential developmental issues on top. Asking people to raise children in those conditions is effectively asking them to run a large, uncontrolled biological experiment on their own offspring, with no way to fully predict the outcomes, and no option to bring them back to 1G and normal radiation if things go wrong, at least not quickly or cheaply. Even if you somehow manage the immediate medical issues, there's a deeper mismatch. Human physiology is the result of millions of years in 1G, under a thick atmosphere inside a strong magnetosphere. Our bones, muscles, joints, senses, circulation, and cellular repair systems are all tuned to that reference environment. Mars gives you thin hair, low pressure, no real magnetosphere, higher radiation, and lower gravity, permanently. You're asking a 1G organism to operate indefinitely outside its design envelope. In the short term, technology can bridge some of that gap. You can use exercise regimens, pressure suits, maybe centrifuges for artificial gravity in small doses. But for a true Mars population, that's not a one-time fix. That's a permanent dependency. Every person for every year of their life needs that support. If you lose the technology or the power base for even a short period, the environment pushes back hard. And the biggest trap is this: you won't really know if Mars is biologically workable for long-term human life until you've already put real humans there for many years. Animal data and models can only take you so far. The actual test ends up happening with people's bodies, and if it goes that far, with people's children. If Mars turns out to be fundamentally bad for human biology over decades, the fix isn't simple. There's no quick way to move a whole settlement back to Earth. You could end up with a population that is slowly being damaged by gravity that's too low, radiation that's too high, and conditions that medicine doesn't fully know how to counter. So by the time you reach this point in the chain, you're not just dealing with one hard problem. You're dealing with all of them stacked up. Unknown gravity biology, chronic radiation, fragile life support, limited medicine, deep isolation, huge engineering complexity, and tight economic limits. None of these by itself is a pure physics says no barrier, but together they start to look like a wall. Which brings everything to the final point. Mars doesn't beat us with one impossible challenge, it beats us by piling many barely manageable ones on top of each other until the whole thing tips from just about feasible into practically impossible. So the real question isn't, can humans reach Mars in a pure physics sense? It's, can we handle all of these risks all at once with no do-overs using the tech, money, and biology we actually have? So after all of this, what actually makes Mars feel out of reach? Is it one fatal flaw, or the way every problem links arms with the others and drags the mission down together? When you look closely, none of the pieces we've talked about are pure hard-stop physics barriers. Distance is brutal, but not infinite. Radiation is high, but not instantly lethal. Microgravity wrecks you, but people do survive months on the ISS. Life support can be built, rockets can be made bigger, a lander can, in theory, be engineered. Psychology can be trained for, medicine can be upgraded. On paper, each individual challenge lands in the very hard but maybe manageable box. The trouble starts when you stop looking at them one by one and start stacking them. You need more shielding to cut radiation, which adds mass, which demands more propellant, which means bigger rockets or more launches, which means more money and more complexity. Longer transit times increase radiation dose and microgravity damage, which pushes you towards wanting faster trajectories which need more delta V, which loops back into mass and fuel. You want redundancy and life support to improve safety, but every backup system adds volume, mass, and interfaces that can break. That again increases the load on your rockets and your budget. Psychological risk doesn't float by itself either. A cramped, noisy ship is more stressful when systems are finicky and alarms go off more often because you're running them near their limits to save weight. A crew under chronic stress is more likely to make mistakes, and those mistakes hit harder in a spacecraft that's already running close to the edge. Medical risk climbs because bodies are weakened by microgravity and radiation, which makes minor injuries more serious and recovery slower, which in turn affects how much work the crew can safely do, which affects how many people you need, which again feeds into mass and life support demands. Each domain pushes the others in the wrong direction. Then there's the stuff you cannot neatly model yet, the unknown unknowns. Apollo taught us a lot about short missions to the moon. The ISS teaches us about long stays in low Earth orbit under partial protection from Earth's magnetic field. Robotic missions at Mars tell us about the atmosphere, radiation, dust, and landing profiles. But a multi-year crewed Mars mission sits in a regime we simply haven't operated in before. It's longer than any crewed mission so far, farther from Earth than any human has gone, using more complex hardware than any previous deep space system. In a system that big and that new, you will discover failure modes that nobody predicted. Maybe it's a slow chemical interaction between Martian dust and a specific seal material. Maybe it's a software timing issue that only shows up when a computer has been running for 600 days without a restart. Maybe it's a subtle psychological pattern that appears only when people have been under delayed communication and partial gravity for more than a year. These are the things that keep engineers awake, because no amount of ground testing can fully recreate the exact combination of environment, duration, hardware aging, and human behavior you get on a real Mars mission. On top of that, you're walking a razor-thin timing line. To make Mars reachable in any practical sense, you need several big pillars to line up at basically the same moment. You need heavy lift launchers that actually work at high cadence, not just in demo flights. You need closed-loop life support that can run for years with very few failures. You need workable deep space radiation mitigation that doesn't turn the ship into a flying skyscraper of shielding. You need ISRU systems that can reliably turn Martian CO2 and ice into propellant, oxygen, and maybe water at industrial scale. You need power systems that can ride out dust storms and long nights. And wrapped around all of that, you need steady will and consistent money for a decade or more. Plus, crews who understand that they are signing up for risk levels far above anything in normal civilian life. If any one of those pillars is missing or late, the whole thing slides. No reliable heavy-lift rockets and your mass budget collapses. No robust life support and your crew survival odds drop below what anyone will sign off on. No ISRU that actually works after years alone on Mars, and you may not be able to get home. No will and funding disappears halfway through development. No money and you can't build or test enough hardware to trust the numbers. You rarely fall from almost there to slightly worse. You fall from barely feasible back into we just can't do this safely right now. So is it truly impossible? From a pure physics standpoint, no. The equations don't say never. You can calculate trajectories, delta V, shielding thickness, and structural loads. Nothing in those numbers absolutely forbids putting humans on Mars and bringing them back. But physics is only one layer. On top of it sits biology that was never evolved for this, technology that has to perform at almost perfect levels for years, industrial capacity that's still too small, and systems that struggle to hold focus for longer than an election cycle. What makes Mars feel impossible right now is that we're trying to run high-risk biology inside uncompromising physics using limited budgets and fragile patience with zero room for catastrophic failure on the first try. Every fix to one problem tends to make another worse. You solve mass with ISRU, but that adds complexity and new failure modes. You solve radiation with more shielding, but that makes your rockets heavier and your launch count higher. You solve psychological strain with larger habitats and more crew, which again pushes mass, life support, and cost. Until we've massively scaled up our space infrastructure, made launching hundreds or thousands of tons to orbit per year routine, hardened life support systems so they're as trusted as jet engines, proven long-duration ISRU and partial gravity biology, and decided, honestly, how much human risk we're prepared to accept, Mars is not the next step in the way people like to say it. It's a step that demands a level of capability, redundancy, and tolerance for failure that we're not even close to yet. So when you hear "we're going to Mars soon" and it sounds simple, remember what's underneath that sentence. You're talking about sending fragile human bodies, built for 1G and thick air, into a multi-year mission where distance, radiation, microgravity, engineering, and psychology all have to behave at the same time with no real do-over. Physics allows it, but everything else around it is what for now keeps Mars feeling less like a destination and more like a hard limit on what our current civilization can actually pull off. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.